Alright, welcome to another session of video log recording. In this, the date is 2025, March 8th. The name of the notebook is Genetic Algorithms Grid Search 3, 40 items. This video follows the one where I did the same thing that I'm about to do, but with 30 items, so 10 items fewer. Or rather, let me put it this way. So far, I've done it only with 20 items, but then I thought, why not try it with 30 items? Why not think up of 10 more items, 20 more items, and 50 more items, and see what happens. Although, and then even then, I didn't think anything interesting would happen, but something did happen. It could be because I'm not doing things right. It could be, something that people already know about. But yeah. So in this notebook, it's 40 items. Everything is the same, except 10 new items were added: gloves, contact lens, tripod, flip-flop, octopus, like a doll, like a plastic doll of an octopus, and a gun. Yeah, I don't have a gun. I don't own a gun. A knife. Why not a knife? If I already put in a gun, imaginary gun, why not put in an imaginary knife? And a mask for to block viruses, COVID virus or whatever, a flu virus, and a rubber band, and a bottle cap. Some useless items. And 10 new weights were also added accordingly. Utility values were added accordingly, and 10 new physical weight values were added accordingly. And therefore the total sum of constraints or physical weights is 8,420, and all the other functions are the same. Here we see hyperparameters. Now that the total sum of physical weights have been have increased because there are more items, 8,420, I again arbitrarily, very whimsical of me, but set that to 6,500. The population size is still 500, and number of items is 40, and so is the genome length. Mutation rate is 3% or 0.03. Crossover rate 0.7, but I don't use that. Generation is 10, but I don't use that right now either. And now that I have everything adjusted, let's see what happens. So first, again, is I'm going to create a list of number of generations from 50 all the way to 3000, and evolve for these numbers of generations. In total, they add up to 91,500. And because again, like I've always said, I'm not going to run these cells on Google Colab because they just take too long. So these are the results that I got when I ran these cells on my MacBook Pro 2024. Bought in 2024, January, the new one. So here are the plots of average of top 20 and top 30 sum utility values of the top 20 and top 30 entities. They oscillate, very usual, nothing unusual here. Yep. So next up is evolve it for 3,000 generations and do that 5 times. And here's the plot. and then this is what happened. We see a huge peak, only for there to be a decline, and then it plateaus out to the right. It never recovers to the peak level. It doesn't. And so does the other ones. It's just that, and this is what I call the dip. The peak minus the plateau level. That's what I call the dip. And the dip is the biggest for this red line, but for other lines the dip also exists. So I evolve it for very long, but for once. So 30,000 generations as before. And when I plot that, this is what happens. See, if you look here, here's the peak, and then it goes down. At every 50 generations, it goes down, and then it never comes back up. Never. Nowhere close. So that's odd. So let's record at every generation for 3,000 generations, but do that 10 times, like we have always done for the past few videos. And this is what we get. There's the peak, and there's the plateau, and here's the dip. And we zoom in, we see what happens. It goes up, and then there's always a point where it rapidly goes up, very kind of dramatically. The slope is quite steep, only for it to come back down, and then plateau outwards to the right, and never recover. So that's odd. Let's do that with different numbers for the population. Don't run it. From 10 entities in the population to 2,000 entities in the population. And then when we do that, here we still see the dip. But so what happened? The purple line is when there are 2,000 entities in the population, and the red line is probably when there are 500. So if there are more entities in a population, the dip is less pronounced, but it still exists. Yeah. And if we zoom in more to something that we can actually understand, this is until generation 100. See, it goes up and it stays. I think this purple line is probably for population 2000. This red one is probably for this one. Probably 500 or something, or 300. Yeah, probably 300 or 500. And if we plot it until generation 300, even the top brown one, where population 2000 is represented, there's still a dip. The plateau is still at a higher level, but there is still a dip. And even for the green one as well, they sharply go down. So it might make sense to think that more population means a smaller dip. So I did another. I made another notebook for that to experiment on that, but not in this notebook. And if we plot it until 500, generation 500, we still see the dip. And we see the dip at about, which is at about 10% decrease, because it's about at 1000, and the dip always stays somewhere close to 900. And if you look closely, this plot is until generation 500, but all these plots are for population 2000, all 5 of them, because I did them 5 times per population. And if you look closely, and you'll find that every plot peaks at around 1000 and then falls and then plateaus at about 900. So the dip is about a difference of 100 summed utility value, which is like a 10% decrease. So this is kind of sad if I could put a sentiment to it. Sad in the sense that what used to be, or what could have been the best, or what were the best, have been lost. That's okay, but it's never recovered. You'll never know what the best was. Thinking that the current is still that the current best is the best ever, which is clearly wrong. Yeah, and sure, there may be ways of preserving these bests, or kind of recording these bests and then bringing them back at something like generation 300. But I don't know if that's well, I can do that, but that's when we know that it is the answer. This happened, all these plots, all these data, and all these entities happened without knowing what a good entity is in this context of the problem set, in this context that the problem set actually provides us. So going forward, it'd be very interesting and very beneficial for me to find out how I can preserve this in a natural way without having to do a lot of artificial or deliberate, not deliberate, artificial, without having to do anything artificial that kind of saves the best one, like that procreate function that always replicates the best one and then leaves it behind. That it would be interesting to know how we can just bring these back, because we never know what is good in this context, and if we do, that will also change, and it would be sad to think that at generation 300 or 400 we may never know what these entities were, what entities gave you this peak. I mean, the plateau means that it's stabilizing, but at the same time it means that this is lost information. And because I don't want to do another video log of this notebook where I did it for 50 items, I'm just going to do that, and you'll see why I want to do this. And in this 1, 20, 30, 40, 50. So in this notebook, again, 10 more items were added, namely item 41 to item 50, so very creative. And some new values were added for the values and for the constraints. So there are 50 values in each. And when I run that, the first one, it oscillates, and there's a huge peak there. See, this is already unusual. The second one, where I evolve it for 3000 generations but 5 times, we see another peak, and it comes back down, which is at around less than 1100. The peak is at about 1200, 11. So this is more than 10% decrease. The dip is even bigger here. And then evolve it for very long, for 3000 generations, and we assess it. As we can see here, it reaches 1200, and the total sum of all the weights are, where is it? Yeah, 10,850, and the total sum of utility values are 1580, 1580, and the hyperparameters the max constraint is 9,000. That is the physical weight threshold. And when we give that, remember it was sensitivity values. The max is when we have everything in the knapsack, it is 1580. But when we evolve it for very long, the average of top entities peaks at just above 1200, and then it falls back down, and then it plateaus outwards to the right. So all this huge peak and this huge difference of the peak and the plateau level, which I call the dip, is a significant loss of information that these entities in these generations never recovered or never got to know about. And if we do this, if we evolve it for 3,000 generations, do it 10 times, and record at every step and plot these out, this is what happens. Same thing. All at this level. The dip is even bigger now. More than 11%, 12, 13, I think about 15% also. We zoom in and then plot everything until generation 250. This is what happens. The peak is more pronounced, and so is the decline. I mean, the peak at this time, they peak at different generations. Like this. So it appears that the longer the genome, the more variance the more variance it causes in the time it takes for the population to peak. Like, for example, it was slightly before generation 50, at 50, after 50, at 70, 80, 100, and then this one's at 160 or something, this brown line. But one common event is that they all plateau. They all fall and plateau. And then there's a dip. And this is when we use, if I were to refer to one of those procreate functions that I have explained, this is the high favoring high, where the weights at which the entities are chosen are computed by dividing the population size by 1, 3, 5, 7, 9, etc., depending on where the entity is in a decreasing order, in a descending order. So the first one will have a population, have a weight of population size divided by 1. The second one will have a weight of population size divided by 3. Third one divided by 5. Fifth one divided by 7, etc. 1, 3, 5, 7. Yeah, fourth one, and 9. It will be for the fifth one. Divided by 9 will be for the fifth one, and etc. And when I do that with different numbers in the population, from population 10 to population 2000, and plot things out, it seems that well, number one, it just took more population to peak at a higher level, above 1300 in this time, which is awesome. But even if it peaks somewhere close to 1300, we still have a dip. Even for population 2000. So, and the dip is still about somewhere around 20% or 15% loss in terms of summed utility values of individual entities. Yeah, and if we zoom in until 20, until generation 70, there's the peak. You start getting the peaks. Generation 100, we got the peaks. Some runs already have gone through the peak, and then they fell down, and then they're starting to plateau out. generation 300, we got the peaks. This blue line is for population 10, so again here we see that a smaller population never is good, at least right now, because it never reaches the decent level of some utility values. This is 10, 50, 100. This is 200. This for 200. I think this orange line is for population 200. Even for 200, it doesn't. It peaks and then falls and plateaus out. There's still a dip. Interestingly, for population 10, there never seems to be a dip. There's only a peak and then it just plateaus. There isn't much of a dip here, but this is bad because we know that it should be way more than 390, because we know that the near best ones go somewhere close to 1350 or something. Remember, this is for 50 items. And here is for generation until generation 500, and all the ones with population 2000, they all peaked close to 1400, and then they fell down to 1100. So 1400 minus 1100, that's 300. So that's about 20% loss. 20% loss of information. So that's what the number of items or the length of genome does it to generating entities. The longer the genome, the more likely it is for there to be a significant difference between the peak and the plateau level, which I call the dip. I mean, I don't know what others call it yet. I haven't actually done that kind of research, but yeah. And I think it will be very interesting to know how to control this dip, minimize it, control it, or eliminate it, or use it to my advantage at certain points in time, or it's I think it's very much worth knowing. So that's that. Thank you very much for watching. Next up, I'll probably be talking about how to mitigate the dip by using some different methods or strategies. But spoiler alert, I haven't been that successful. But anyway, that's about it. I only did that with 40 items, but I don't think I've been that successful. So thank you very much. See you next time. Bye.